Welcome back again. This is going to be part number 4 of collective communications in MPI. So we're going to continue from where we left off. We already talked about scatter in both intra and inter communicator scenarios. Now we're going to go with MPI scatter V. Similar to MPI gather that we had an MPI gather V version, which gave us sort of flexibility to have an array for receive counts and also an array for displacements, not in bytes, this is super important, but in terms of number of elements with a specific data type. This time, scatter also has a version scatter V, which this version gives you flexibility to have send counts, which are arrays, and then it gives you also flexibility to have displacements, again, not in bytes, but in terms of elements. So you see the symmetry. So I'm not going to spend too much time on this because you already know. If you don't know, then please go back and watch part number 3. But I'm not going to spend more time on this. So we have one example here, MPI scatter V. But before jumping into that, let's see if we have, again, we have something as if this is happening, root executed and operations and send operations. This time the displacement is going to be with this sort of array. And then each process also receives it with basically calling a MPI receive. This is as if. This is not exactly what is happening behind the scenes. Again, all arguments to function are significant on the root, but some of them, specifically these, the first 4, are not significant on other processes. So that's what it wants to say here. And then we have, of course, you can also have this MPI in place option available. We're going to see an example in a second. And let's take a look at the example. Of course, Final Cut is also rendering stuff from previous episodes. So MPI scatter v.c. So again, the same story. We have a buffer with integer and we have a buffer in C style string, the problematic C style strings. And then in this case, we are having these displacements again. And we are having an array for send counts, the same displacements and string counts. Like when I say the same, it means that they're going to be arrays. These two, the first two, are associated with this with the send buffer and the receive buffer, and these two are associated with the C style strings that we want to pass around. Then, of course, you need to populate it with sort of let's say based on their rank, and then counts is everybody's gonna send only basically 1. Not everybody, actually root is only gonna send 1 value to every other process. And then the same way, but the count is gonna be 10 because we have 10 characters for the string, and displacements is gonna be I times 10 based on the rank again. Rank 0 is the one responsible for allocating the buffer, both for send buffer of the integer and send buffer of the string. And this is the whole size. Notice that we use the whole size because we are talking about an intra communicator scenario. Again, we populated uniquely with some data. We print the original data. And then for the string, we also populated uniquely. But this time, this %d doesn't signify the rank of the process, but it only signifies sort of this loop counter I. Then we print the original data again. And we use the scatter v. For the integer, we send with the send buffer, and we receive with the receive buffer. But and also note that we are using MPI com world, as I said, intra communicator scenario. But for the C string style, since we want to see also how MPI in place works, then in receive buffer, we actually use MPI in place for rank 0, which is the root process. And for all the other processes, we simply use the receive string buffer. Okay. And then process 0 is going to print its information, and all the other processes are also going to print their information. So let's go back. MPI CC, MPI scatter v.c. and MPI run. So again, you see that the root process has this information, this array of integer, and also it has an array of these C-style strings with one number associated to that. And you see that proc 0 has information 0, hello 0, and then proc 1 has its own share of the scattering, which was from root process or process 0, which is 1 from the integer array and hello 1 from the string C-style string array, and all the way down to process number 7. So very straightforward example, very beautiful one. Again, we are going to consider the intercommunicator scenario with MPI scatter v inter. So let's take a look at it. MPI scatter v inter. Same scenario here, no comment on these things. We're going to see them in chapter 7. But here we have the displacements. The differences here is that the size of these displacements and the counts is going to be the size of group B processes. So that is world size minus local size. And we allocate again properly with their rank, based on their rank, and the count is always going to be 1. Notice that here we don't have any C-style strings because we wanted to have this example as simple as possible, because in intercommunicator scenario we already have a lot of stuff regarding creation of those intercommunicator and groups like group A and group B. So that is why I kept it as simple as possible. Then again, this thing is basically, I forgot to mention this here as well. So this is proc 0 or root proc in group A. I'm going to save it, which needs to allocate the proper sizing for that integer buffer, which is going to be corresponding, the size of that sort of buffer is going to be corresponding to the size of all the processes that we have in group B. And then we uniquely fill those information. We also print the original data in the root process of group A. And then this is what you always need to take care when you are working with intercommunicators, that the root process in group A needs to pass in MPI root as this root element. And 0 is the root element that all the MPI processes at group B needs to send as an argument here. And all the processes in group A, which are not the root process, they're going to send MPI proc null as this root. And then we call MPI scatter V. So this is, of course, the significance is here that we are not talking about MPI com world, but we are talking about intercommunicator. And then finally, once the data is scattered from a root process of group A, group B, which is color 1, is going to print the information that they have received from a root process of group A. And then this is the root process that needs to free the send buffer, because it basically allocated with malloc dynamically. MPI CC, MPI scatter V, inter, and MPI run. So you see again, the root process in group A has a send buffer of 0, 1, 2, 3. The size of this array is exactly equal to the size of the processes in group B. In group B, we have processor number 4, 5, 7, 6. So 4 processes. That is why we have an array of size 4. And every process also gets its share of the scattered data from the root process of group A. A beautiful example. Now we move on. So these examples, we have our own examples. We don't care about these. The next thing on the line is gather to all. So this is all gather. And similar to gather, this is a gather operation. But in gather, you remember that the root process was the only process that got all the information, absorbed all the information, and printed all those information. But all gather has the difference that every process basically receives the result, and it's going to print that result. Okay, we have the same drill: send buffer, send count, send type, receive buffer, receive count, receive type, and then we need a communicator. Notice that here, between receive type and communicator, we don't have a root element. Why we don't have a root? Because as I said, everybody is gonna basically contribute in sending the results, and everybody is gonna receive all those results. Okay. So MPI all gather can be thought of as MPI gather, but where all MPI processes receive the results, that's the difference, instead of just one root. The block of data sent from the jth MPI process is received by every MPI process and placed in the jth block of the buffer in the receive count. The type signature associated with send count send type at an MPI process must be equal to the type signature associated with receive count and receive type at any other MPI process. If communicator is an intra communicator, the outcome. Okay, this is again as if what is happening. So we're not going to comment on that one. So again, order of data in buffers should be based on their rank. So this is what signifies there. You have the option of in place when you're working with intra-communicator scenario. Again, you're going to use the MPI in place as the argument for send buffer. This means that the send count and send type are going to be basically dummy, or they're going to be ignored. That's it. And this is intercommunicator. So let's take a look at MPI all gather. So MPI all gather. Let's see. Okay, so what is the difference? The difference is that you remember that receive buffer, only the root process was allocating the proper size. But here, since everybody is participating, and everybody wants to also receive the data, then that is why we have this call not in a sort of if statement that we say if rank equals 0. But everybody is going to allocate the proper size. What is the proper size? Is the size of the processes that you have, let's say 10 or 8 or whatever, times the size of the integer. This is for the let's say integer array, which is uniquely sort of initialized with the rank of each process. And then to add one more level of complexity, we have a C style string again with 10 sort of characters available to it, but not necessarily uses all the 10 characters. In fact, it uses only 2, 4, 6, 7, including the null character, the terminating null character. Again, the receiver string is the same. It should allocate, it should call this malloc on all processes, not only on the root process. Then we have MPI all gather. We pass in all the necessary information here. Notice that the communicator in this case, because it's an intra communicator, it's going to be MPI com world. And for the string, since we want to use MPI in place, we are responsible to fill up the receive count for the 0th, let's say, block, which is the first 10 characters of the receive string in root process. And then take a look at this thing that we have the root process printing the receive buffer for the integers, printing the receive buffer for the C style strings, and then we have rank 1 also printing its stuff. I mean, you can also print other processes as well because everybody is gonna receive the same results, but since it's gonna be messy, I only put processor 0 and processor 1 to print their own results. And then notice that since everybody now dynamically allocated, so everybody needs to call this free, not only proc 0. So MPI cc, MPI allgather.c, and MPI run. And then you see that the root process has this information, and exactly similar to that, process number 1 gets the same sort of information. So that is the significance of all gather. Now, what happens if we have an intercommunicator scenario? Again, you already know that what's gonna probably happen. So let me read it. It says each process of one group, group A, contributes send count data items. These data are concatenated, and the result is stored at each MPI process in group B. Conversely, concatenation of all those contributions from processes B are going to be stored in all processes in group A. So this is the semantics of the intercommunicator scenario. So let's go with all gather, inter. Same story with the intercommunicator, but this time you see that all the processes which are in group A, they're going to have their receive buffer, which have the size of all the processes in group B, and all the processes in group B are going to have the sizes which is equal to the sizes of group A. So that is why we have different malloc calls for receive buffers for group A and for group B. So that is what it means. And this block of code basically shows the semantics of all gather in intercommunicator scenario, because you see that group A is allocating based on the size of group B, and group B is allocating based on the size of group A. And you call all gather similar to the previous call, but this time the only significant, let's say, matter here is that we are not using the MPI com world, but we are using the intercommunicator between group A and group B. And notice that here we have for color 0, so this is all the processes in group A, they're going to print their own results. Notice that for complexity of intercommunicator scenario, we have removed the C style strings. We only work with the integer that we are sending. And all the processes in group B, they're going to send their own results. Or they're not going to send, they're going to print their own results. And since the receive buffer is dynamically allocated, everybody needs to free that. But the size is different, as I said already. The size is different. This one is the size of group B, and this one is the size of group A. And by the way, if you are using even numbers, if I have 10 processes, then group B and group A are going to have the same size. So this is not that significant. But if I'm using odd numbers for processes, let's say 7, then one of these two are going to have unbalanced, so one more process, let's say. That is the significance, that they are not going to be equal always. So let's go with MPI CC all gather inter. Whoops. I need to say MPI all gather inter and MPI run. Now you see that that integer sort of buffer was 4, 5, 6, and 7. So you see all the processes, since we have used 8, processes 0, 1, 2, 3 are going to be in group A. Processes 4, 5, 6, 7 are going to be in group B. So you see that processes in group A, they have information from group B. So these are uniquely occupied by the rank of those processes. So you see, that's literally the semantics. 4, 5, 6, 7, all the information collected from group B. And processes in group B, they have all the information from group A, which is 0, 1, 2, and 3. So it's a very beautiful example. That was the intercommunicator scenario. Now we can move on. So again, Allgather has a V version, which same drill. It gives you sort of flexibility to have, let's say, custom displacements and receive counts. You see that receive counts is going to be an array, and displacements is going to be an array. Again, this thing is not going to be in bytes. It's going to be in terms of number of elements. I'm not going to comment on those. Again, you have the option of in place, and we're going to see in the example with C style strings. Let's take a look at this allgather v. So MPI allgather v.c. Everything is going to be the same, but we're going to have displacements this time for the integer buffer. And we're going to have sort of an array for the receive counts of the integer buffer. And this is going to be the displacements for the C style string buffer. And this is going to be the counts for the C style string buffer. Again, you're going to properly initialize the displacements. So displacement is going to be based on your rank. So that is why we use that. And counts, everybody is going to basically send only one value. And notice that the only difference is that the string has 10 here, because of the counts that this thing is 10, the send string. And for the displacements also, it's going to be I multiplied by 10 because of the size of that buffer. And then we call MPI all gather v. We pass in all the proper arguments. Notice that the only important thing here is that we pass an MPI com world, because this is an intra communicator scenario. And since we want to use MPI in place in the send buffer, then we are responsible to properly fill in the receive buffer of every rank. So this is going to be called with all the processes. But all the processes are going to fill up their own rank. I hope you understand the significance of this statement here. And we have MPI all gather v, which uses MPI in place this time. And then we have displacements. That's the difference. And we have also an array of counts. And then you see that rank 0 prints its own information, and then rank 1 also prints its own information, and we free all those dynamically allocated resources. MPI CC MPI all gather v, and MPI run. You see that beautifully. You have again this integer array with 0, 1 all the way until 7, and then you have a string like this one, and everybody, like if I was printing proc 2, proc 3, proc 4 up until proc 7, all of them have the same integer array, and they have the same sort of C style string array. Okay, a very beautiful example in intercommunicator scenario. These examples, we have our own examples. Okay, now we go to scenario of all to all, scatter and gather. If you remember this thing, scatter and gather, was sort of the case that we were talking about. It had the name of complete exchange. So we have an example, MPI all to all. Let's see. You see that we have send buffer, send count, send type, receive buffer, receive count, receive type, and we have a communicator. Again, we don't have a root here because this is going to be an all to all. So this is going to be a complete exchange. So this means that every process is going to have an array which has the size of all the MPI processes that are involved. And every process is going to populate that array with its own information. And then after this all to all, we're going to have a mishmash of the information from, oops, the 23 minutes mark is done. I'm going to finish my sentence and then we're going to go to the next episode. So every process is going to have a mishmash of all the information from all the processes in the communication. So probably we don't have enough time to go to see this example. I'm going to continue in the next sort of episode.